Hello, people. We're going to, for most of us, continue our discussion of simple harmonic oscillators and/or simple harmonic motion um, by representing the position of a simple harmonic oscillator as a function of time. All right, now our simple harmonic oscillator is either a pendulum, where we are measuring an angular position as a function of time, or it's a mass on a spring where we're representing a linear position, how far this object is from its equilibrium position here. Maybe it's over here now, and this is a distance x. So one of those two displacements, either an angular or a linear displacement, can be represented as a function of time. Well, in this case, as a cosine curve. All right, we're going to say at the beginning, at time 0, we displace this thing a lot, and then we let it go. And what this object does is, well, it moves back through equilibrium, moves fast back through equilibrium, then gets somewhere and turns around and comes back and moves fast through equilibrium and goes out to another maximum, turns around and comes back. And so we get this, this characteristic motion that has to be represented by a cosine or sine curve. And I'm going to choose the cosine curve here because that's what this one actually is. And we're just going to say that in general, why don't we, if we talk about the pendulum, we can say that the position, the angular position theta, can be expressed as, well, a cosine function, and which has some amplitude a, where this is the amplitude a. And then it's a function of time, and we write it as omega times t. That's what's called the angular frequency. Angular frequency. Now that angular frequency dictates how quickly this object goes through one cycle, all right, or comes back to its original equilibrium position. And it's related to the amount of time it takes to do that. And it's related this way. We say that omega is 2 pi divided by the period. So for my folks that are doing a lab, if you didn't calculate your angular frequency that way, by first measuring period, which I did tell you to do, go back and do so now. If you found a different equation to find omega, please don't use that now. Please go back and you'll show me where you've done these calculations. All right, so here's the deal. Most of you have seen this in class, but worth going through again. We want to draw the velocity of this object as a function of time, knowing that, well, here's its position as a function of time. Well, we have a graph of position and time, and we want to use that to make a graph of velocity in time. Well, remember, how do you use an xt graph to find velocity? Well, slope. Slope of xt is velocity. So this says that, well, the slope of this curve at that instant is 0. The velocity is 0. The slope at this instant, big and negative. Velocity, big and negative. Slope at this instant, 0. Velocity, 0. Slope at this instant, big and positive. Velocity, big and positive. Slope is 0. Velocity is 0. Slope, big and negative. Velocity, big and negative. And so on, and so on. Oops. And so on, and you get the idea. So the velocity as a function of time looks like this. Well, that's kind of interesting, isn't it? It's actually the same thing as this, just shifted over a little bit. This is actually a negative sine curve, right? Now we can use that graph of velocity in time to plot the system's acceleration as a function of time. And how do you use a VT graph to find acceleration? Well, the slope of of vt is acceleration. So this says that early on here, slope big and negative. Slope 0. Slope big and positive. Slope 0. Slope big and negative. Slope 0. And so on. 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 All right, so we graph this, or we connect the dots, I guess I should say. And we get that. And notice that the acceleration of this simple harmonic oscillator is the direct opposite of its position, which we defined as really the defining characteristic of a simple harmonic oscillator, or really the defining characteristic of simple harmonic motion. That acceleration is directly related, but just in the opposite direction. It's directly related to its displacement from equilibrium. Right? So these graphs really demonstrate that that has to be true, and it's actually the sine and cosine functions are the only ones that can make this happen, where acceleration will turn out to be the same exact thing, just in the opposite direction as the position. Now, when I say same exact thing, it's not really the same. The size of these amplitudes are a little different, or can be different, but we'll get to that. All right? Well, this has its... You can talk about this in a couple of ways. One is just this way, and using what we know about slopes of graphs and what they tell us. But it also has a foundation in calculus, which says, calculus really talks a lot about one major thing that calculus talks about is what's called the derivative of a function. And what people mean by that is a couple of things, but really it talks about an instantaneous rate of change. Well, rate of change graphically is really about slope. All right, and the deal is, with simple harmonic motion, since, well, what we said, this acceleration is constantly changing. And it does that because the force exerted on the simple harmonic oscillator is constantly changing. Right, and so these aren't nice constant forces that give things constant accelerations like an object in free fall. All right, these are objects where their motion, the force that creates an acceleration, is constantly changing. So for us, we really need to be able to talk about, well, what's the instantaneous rate of change of, well, in one case the position, or the other case the velocity. So really what we're talking about is, what are the derivatives of each of these functions? All right, so if a derivative really talks about the slope, well, we know that velocity is kind of the slope of a position-time graph. So velocity, from a calculus standpoint, is the derivative of position. And then we say, quote, with respect to time. Or we can write it like this. You write it as, well, we're used to seeing this, delta x over delta t. Well, what we say is, instantaneously, delta t has to get super duper small. So we say it's like a little tiny delta t. And therefore, there's a little tiny delta x. So we say that velocities, well, dx dt. That's what people say, dx dt. All right. Well, acceleration is, since that's the slope of a vt graph, that means it's the derivative of velocity with respect to time. Or the second derivative of position with respect to time. Oh, wait, well, that's what goes here. Let me say this, that acceleration is the derivative of velocity with respect to time. So we can say that acceleration is, well, we're used to saying delta V over delta T, but if we're talking about instantaneous rates of change, we really say that, well, it's like in a little tiny interval of time, there's a little tiny change in velocity. So we say that A is dV dt, right? V is dx dt. Well, this is the same thing as saying, well, since velocity is the derivative of position with respect to time, it's the same thing as saying that acceleration is the second, the second derivative of position with respect to time. Okay? So acceleration is the second derivative of position. So that means that the second derivative of a cosine function, remember, here's a cosine function. Come on. There you go. Here's a cosine function. Well, here's its second derivative. Right? Acceleration is the second derivative of position. So here's a cosine function for position. The second derivative is, well, what's this? Apparently it's, well, a negative cosine function. Right? Cosine function starts at a maximum and, decreases and gets to a minimum. And this starts at a minimum and increases, gets to a maximum. So what we're saying here is that the second derivative of a cosine function apparently is a negative cosine function. And so it's really the only function, sine and cosine functions are the only functions that work that way, where you take their, what you end up doing is taking a function's second derivative, and what you get is the original function but negative, or something proportional to the original function but negative. Remember, that's what we said has to be true for any simple harmonic oscillator. We said the defining characteristic of a simple harmonic oscillator is that acceleration is proportional to position. Well, also, and in the opposite direction. Well, the only function that allows that to happen is a sine or cosine function. All right? And so, for my guys, that's why we represent the motion of simple harmonic oscillators with sine, cosine waves. Yeah, because the only function where the second derivative is proportional to the function itself is a sine or a cosine. Other functions, mathematical functions, just plain old don't work that way. Now, if you have no basis in calculus, you have to take this with a grain of salt, I suppose. But it's worth talking about. All right, so for my folks analyzing pendulum data, first, we got to agree on the following. That here on the top is position versus time. All right, and so that means we can express the position, let's say it's of our pendulum, as a well, why don't we say a cosine function? Cosine, well, where there's some amplitude and some angular frequency, and the position depends on time. The position depends on, well, the original displacement, the amplitude. It depends on the system's angular frequency, and it depends on how long the thing's been swinging. Okay? And we also said a while ago that we can relate the pendulum's position and acceleration with the following. We said, we came up with that alpha is negative g over L times theta. That came from our free body diagram, net force analysis of the pendulum. Look back in your notes. Okay? All right, so we're going to use both of those. And here's what we got to say. Well, if we want to talk about the pendulum's velocity, v, well, actually, you know what? It's an angular velocity, so it's an omega. Now, this is angular frequency. This is angular velocity. They're sort of similar. They're both measured in radians per second. This omega here is a vector angular velocity. This omega here is a scalar angular frequency. Kind of a, they're sort of the same, but sort of not. But if we want to talk about the pendulum's velocity, well, dig it. Like we said, first of all, it's the first derivative of the position time function. Or if we look at it, here it is in blue. Here's the angular velocity versus time. And this is, let's see, well, that's a negative sine curve. A real sine curve starts going upward and then comes down. This is a negative sine curve. So what it turns out really is when we say that omega is d, in this case, d theta dt. Well, theta is this. We showed you that it's really a negative sine curve. So it looks like this. The rule, though, when you take a derivative, especially when you take a derivative of a function like this with respect to time, what you end up doing is pulling out or multiplying the function by an omega. You got to take my word for it. If you're not in calculus, take my word for it. Fair enough? Okay. And then if we want to look at the pendulum's acceleration, well, it's angular acceleration, alpha, that's d omega dt. And check it out. Well, here it is. Oops. Here it is. Like we said, what's this function here? Well, it really is a negative cosine curve, right? So that's, and here's how it works. You take the original function, you take that negative omega a, well, it's a, like you said, it's a negative sine curve. But the rule again is we got to take this part, and when you take the derivative of that part with respect to t, you pull out another omega, so you multiply again by omega. And so what we get is that acceleration is negative omega squared a sine omega t. Okay? So check it out. We now have something we can plug in to here, and we have something that we can plug in to here. So instead of writing alpha, I'm going to write negative omega squared a sine, crap. Some of you caught this a minute ago. This is not supposed to say sine. That's supposed to say cosine, right? Let's look back at our graph here. This is a negative cosine curve. Agreed? Sorry. So that goes here. Cosine omega t. Good. All right, so here's alpha. Negative omega squared a cosine omega t. Equals negative G over L theta. A cosine omega t. And look, yeah, the acceleration is proportional to the displacement, the position. So much so that these whole things can go away. And these two negatives become a positive. And what we get is that this is the angular frequency is that. So that means that the angular frequency is the square root of G over L. So how fast does a pendulum swing back and forth? Or how fast does it, how many cycles does it go through per second? Well, that depends on a couple of things. Oops. It depends on the length of the pendulum. Oh yeah, you just did that experiment. It also depends on G, but luckily in your house where you did this lab, G's constant. All right? Let's use that. Because you plotted omega versus L. You should have. And what you get is that it looks like that. Well, we just said that omega is the square root of G over L. So look, it's kind of like, it's kind of an inverse thing. Well, omega, you could write this as the square root of G times 1 over the square root of L. Agreed? So it's kind of an inverse thing, and you know inverses have this general shape. But what I want you to do is plot a straight line graph. Straight line graphs have the form y equals mx plus b. Well, we have the equation omega is the square root of G times 1 over the square root of L. So your job is to do some manipulation of your raw data and come up with a straight line graph. So the question is, what do you put here? It ain't L, because if you just put plain old L there, here's what you get. You get a graph that looks like this. Everything you need to know is written on this slide. What goes here? And the question is, what can you now use this graph to find? All right, this graph. You can use it to make an experimental determination of something interesting. All right, so 1. Plot two. Find something interesting. Okay? So as we said, this is the graph you already have, based on plotting omega versus L. Angular frequency versus L. Keep angular frequency here, but plot it versus something else to give you a straight line graph. Make that graph, and then second, use that graph to find something interesting. Use Excel, or don't. If you want to do it by hand, but you might as well use Excel. All right, come back tomorrow with that stuff done. Okay? Okay. Adios.